Hi, Algebra 1. So today we're looking at section 3.3, Systems of Linear Inequalities. So yesterday we solved systems of linear equations by graphing. And then the day before we learned how to graph linear inequalities, just plain ones. Today we're looking at systems of linear inequalities, and it turns out the only one that I know of, at least, the only real good way to show us a solution to a system of linear inequalities is by a graph. So that's what we're going to focus on today. But before we get there, just realize that you can oh, and by the way, yeah, you might want to take a look at our objectives here. We're going to check solutions, graph, write systems of linear inequalities. That one's kind of interesting. You'll see in a bit. And then we'll do an example problem for a real life situation that's kind of funny. So what we're going to do is check first here, tell whether each ordered pair is a solution of the system. So to check, we'll do like we've been doing the previous days. You're going to carefully put 5 in for y and 3 in for x. And you'll simplify it, and you'll ask yourself, well, is that true or not? Is 5 less than 6? Yeah, it's true. So that one worked out. But to be a solution of the system, it's got to be a solution to both of them. So we'll check over here. Not bothering to put parentheses around there because there's no multiplication. So anyway, and I get 5 is greater than or equal to 4. Is that true? It is, it's true. Since it's true for both, then that means that yes, 3, 5 is a solution to that system. Okay, let's try 2, 0, but it's the same system. 0 less than 2 times negative 2. Be careful when you substitute things in. Make sure you get your negatives and everything. I get 0 is less than negative 4. Class, is 0 less than negative 4? It is not. 0 is actually greater than, so this is false. This is false, which means we know this was not a solution to this system. It didn't satisfy the first inequality, so therefore it won't satisfy them together. So that's false, so the answer is no, this was not a solution of the system of linear inequalities. Okay, so now let's get to solving a system of linear inequalities by graphing. And again, I'll just say this is the best way I know of to actually present the solution of a system of inequalities. And all you do is you graph both of them. So we'll start out by graphing y is less than or equal to 3. Well, we graph the borderline first. Our borderline is going to be y equals 3. Y equals 3 is a horizontal line at 3. And I made it solid because it's less than or equal to. Because it's less than or equal to 3, I'm going to shade below it. But I'm going to shade lightly. Because it turns out what we're going to do is we're going to shade both of these things, and where the shading overlaps, that is going to be solutions to both inequality. Okay, so we're actually going to be looking for where it overlaps. Okay, let's graph the second one. Oh, it's in slope-intercept form, so our slope is 1 over 1, our y-intercept is 2. Start with our y-intercept and then go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Down 1, back 1, down 1, back 1, down 1, back 1. And then use a straight edge probably. I like to use straight edges. That one I had a line to trace, but we're gonna make this dashed because it's not equal to, so it's gonna be dashed. What's funny is these points kind of make it look like it's dashed already, doesn't it? And I'll keep going here. Okay. Well, class, on this one, we could use a test point, but I think it's wise to get into the habit of realizing if you've got y by itself, you can tell which way to shade. This says greater than, so we're going to shade above. Now, normally I would shade everything above, but our final answer is going to be where the shading overlapped, and it overlaps right in this triangular area is where the shading overlaps. So I'm going to get in there and darken that in to show that that's my final answer there. Everything in this darkened in area, because it's where the shading overlapped, everything in this darkened in area will be a solution to this system. If you want to, you can go back and erase the other shading, which is what the book often does. They won't show the shading that wasn't actually part of the answer. I feel like if you do a good job of darkening in your overlapping shading, that it's pretty clear to everybody which answer it is, where your answers are. So class, be careful with this. Somebody might say, well, hey, isn't 0, 2 a solution to this system? And notice 0, 2 is on the dashed line. It would not be a solution to the system. It would not be a solution to this. It would be equal, but it has to be greater than. So anywhere you're on the dashed line, not going to be a solution of the system. If you're on a solid line, you're good. And of course, if you're on the shaded areas, you're good as well. Okay, so if you want kind of rules to this, step 1 is to graph both inequalities, shade lightly, and then darken in where the shading overlaps. That's going to be your solution to the system. And like I said, that to me is kind of the best way to illustrate solutions to inequality systems. Okay, let's try another one. On this one, they're not in slope-intercept form, so we could solve it by finding the x and y intercepts, but I'm going to do slope-intercept form. I think that'll be pretty easy. I'm going to subtract that 2x over, and I'm going to get y is less than negative 2x minus 1. And I'm going to subtract this 2x over and get y is greater than negative 2x plus 3. And now I'll be able to get slope, y-intercept for each one. And I'm ready to graph them. Y-intercept of 3, down 2 over 1, down 2 over 1, down 2 over 1. Up 2, back 1, up 2, back 1, up 2, back 1. Oh, and I made a common mistake. At least it's a common mistake for me. I drew a straight line. I drew a line, but it should be dashed. I drew a solid line. Maybe I should say it that way, but it should be dashed. At least I caught my mistake though, so that's cool. So make sure it's clearly dashed. And then that's still not real clear on the camera, but yeah, it's dashed. And it's gonna continue forever. That's our boundary line. But then it says y is greater than. That means we're going to shade above it. But I'm going to shade lightly because I'm not done yet. For the other equation, we've got a y-intercept of negative 1. And we've got the same slope as the other one. So these are going to be parallel lines, which is pretty cool. Down 2 over 1, down 2 over 1, down 2 over 1. Parallel to our other line. Up 2, back 1, up 2, back 1, up 2, back 1. And this one's going to be dashed as well. So I'll make sure to do that right away. it's easier to not have to erase. So, yeah, dashed line. And from there, it says that we're going to shade less than. So we could do a test point, but less than means we're going to shade below this line, below it. Well, class, our solution is where the graphing, the shading overlaps. Since it doesn't overlap here, that means we have to write no solution. And hopefully that was a surprise to you and you didn't read that up above. I kind of hate that when they tell you. But yeah, it's good. I think it's more fun to discover. But yeah, if the overlapping if it doesn't overlap, then there's no solution. And it's important that you write that, because if you don't write that, then somebody's going to look at this and say, oh, look, I've got solutions in this shaded area. I've got solutions in this shaded area. So yeah, write no solution when that happens. And that's our first exposure to no solution. Yeah, it turns out systems of equations and inequalities can have no solution. They can also have infinitely many solutions. We haven't seen that yet. But yeah, they can also have that as well. But yeah, our first time of seeing a no solution one, the shading did not overlap. Now, if one of these inequality symbols had been flipped, we totally would have had shading overlapping and stuff like that. But in this case, it wasn't, yeah, no overlapping. Okay, example 4 is kind of interesting. It's writing a system of linear inequalities from a graph. Well, class, I want to be clear here. They just shaded where it overlapped, but if you want to think of like, the shading would have been above this line and to the left here. I'm just kind of filling in that just so it becomes really clear which way it's shading for each of those. Basically, you write an equation for each of these lines. The vertical one is going to be kind of easy because that's just x and 3. Normally it'd be x equals 3, but because we're in inequality here, I'm going to pay attention to the shading. The shading is to the left of that line there. Yeah, I don't know. I think I may get rid of that so it's not confusing. But it's shading to the left, and that means it's going to be less than. And because it's solid, we'll give it an equals to on it. And then for our other equation, let's use slope-intercept form. Our intercept's -1, our y-intercept's -1. Our slope is up 2 over 3 will get us back to the graph. So our slope is 2 over 3. So that means we got y, and it'll be 2/3 x minus 1. And then I got to decide the inequality symbol. It's shaded above this line, above it. So it's going to be greater than. It's dashed, so we leave that alone. And we are done. We wrote a system of linear equations from a graph. Let's try the other one here. We'll start with this one. Our y-intercept is 0. Our slope is 1, up 1 over 1. So we'll have y, x. Slope is 1, so we just have 1x plus 0. Don't need the plus 0. Pretty basic. And because it's shaded below, we'll say less than and no equal sign because it's dashed. Our other equation is horizontal, so we would just say y, and it's above, it's shaded above, so we'd say greater than. It's solid, so we make it equal to -2, and we're done. Take your time with those. They can be a little bit, nerve-wracking maybe. I don't know. Remember, think about the equation of the line first, then decide what the inequality is. Okay, our last example is an application problem. And this seems kind of like confusing at first. It says you have at most 8 hours to spend at the mall and at the beach. You want to spend at least 2 hours at the mall and more than 4 hours at the beach. Write and graph a system that represents the situation. How much time can you spend at each location? This is an interesting problem, and it's kind of hard to make sense of, I think, until you graph it. But first things first, we've got two equations here. We're trying to know how much time we spend at the mall and how much time we spend at the beach. So I'm going to make y the time at the beach, x the time at the mall. And it says right here, heck, time at both of them needs to be at most 8 hours. So less than or equal to 8 hours. You only got 8 hours to go to both, okay? You got 8 hours to go to both. But then they also say you want to spend at least 2 hours at the mall. At least 2 hours. That's greater than or equal to. At least 2 hours at the mall. At least 2 hours at the mall. And at more than 4 hours at the beach. Interesting. Okay, I think we got everything covered. So now let's graph this. I'll go ahead and get y by itself. Y is less than or equal to, we'll subtract the x over, plus 8. So our y-intercept's 8. 1, 2, 3, 4, 5, 6, 7, 8. Make our y-intercept, and then down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Okay. Will it be a solid line or a dashed line? Well, it's got an equal to, so it's going to be solid. And then for this other equation, that's going to be vertical at 2, and it's going to be solid. Vertical at 2, solid. Oh, I need to think about shading, don't I? Less than, that's going to shade below. And I shade lightly because I got more to do. On this one, it's x is greater than to the right. So far, I've got this triangle as being my solutions, but I've got one more criteria that needs to be met. Y is greater than 4, so we go to 4, it's going to be horizontal, it's going to be dashed, and because it's greater than, we're going to shade up. So our final answer is in this area right here. Fascinating. Okay, I'm going to zoom in a little bit. So they want to know, well, how much time can you spend at each location? Anywhere in the shaded region or on solid lines that are adjacent to a shaded region will be a solution to this system of equations or inequalities. It will be a solution. So I'm thinking, but anything on dashed would not work. So for example, we couldn't spend 3 hours. This is the mall. This is the beach. According to the criteria, we could not spend 3 hours at the mall and 4 hours at the beach because they want us to be greater than 4 hours at the beach. You see what I'm saying? But we could do 3 hours at the mall, and we could totally do 5 hours at the beach. We could totally do that because that's on that line there. We could also do 2 hours at the mall and 6 hours at the beach. We could do 2 hours at the mall and 5 hours at the beach. We could do 2.5 hours at the mall and 4.5 hours at the beach. You guys see how this works? Anyway, I think that's kind of cool. Have a good day.